All right, we're gonna see if I can get the video recording to work again because it it was giving me grief all last couple of days. Hey, look, I wrote something and it showed up on the screen. Awesome. All right, so this is the 2019 administered FRQ problem number 1 that we're going to take a look at. It is a short answer argument sort of problem that asks you to consider some equations, but not necessarily do any formal calculations. But it will ask you to maybe look at a graph or create a graph. So in this problem, let's go ahead and scroll down to it. We'll go ahead and take a quick look at the whole thing, and then we will go ahead and work it out. So to start with, it's always a good idea when you're reading a problem to do a quick once through, and then as you go and read through, pull out information that seems important so that you don't have to reread the entire paragraph. In this case, there's a big brick of text there, so we want to try to pull out as much as we can. It says identical blocks 1 and 2 are placed on a horizontal surface at points A and E respectively. The surface is frictionless except the region between points C and D. So everywhere except for C and D is frictionless. I'm going to go ahead and label that there's friction there. That seems important. So there's only friction there. Everywhere else is frictionless. Then it says where the surface is rough, beginning at time TA, block 1 is pushed by a constant horizontal force from point A to point B by a mechanical plunger. So this little plunger pushes this whole distance A to B. All right, well, I'm going to put a little note there that zone right there has a force acting on it, just that zone. It says that at point B, block 1 loses, upon reaching point B, block 1 loses contact with the plunger and continues moving to the right along the horizontal surface toward block 2. Block 1 and block 2, block 1 collides with and sticks to block 2 at point E, right there, after which the two block system continues moving across the surface, eventually passing point F. So that would be looks like a perfectly inelastic collision or a sticky collision. And well, that's pretty much the crux. That's everything that's in that paragraph that we could want. What they're going to ask us to do with that is on the axes below, sketch a speed of the center of mass of the two block system as a function of time from TA to point F at time TF, and at the times at which block 1 reaches point A through F are indicated on the graph. So they show you how much time it took relative to go from one place to the other. We want to graph speed versus time for the center of mass. We'll get to that in a second. And then part B, which that's the end of it, part B, is the plunger is returned to its original position and both blocks are removed. A uniform solid sphere is placed at point A as shown. The sphere is pushed with the plunger from point A to point B, just like the block number 1 was, with a constant horizontal force that is directed towards the sphere's center of mass. That's important. In the picture here, it doesn't quite look like it. If I kind of draw it off to the side, it looks like here's the plunger and here's the sphere. And if that's my plunger, you might think that it's pushing on the top half of the ball, but it's not. They're saying it's pushing on the center of mass of the ball. It's not pushing on the top. That's an important little detail. Oops, didn't want to delete all that. So I'll leave that little blue line, no big deal. So we want to make sure that we think about that, but then they're asking us at which point does, if any, does the sphere's angular momentum change? So when is there going to be a change in angular momentum, and explain why? All right, so two very different parts of the question, but let's go up here and take a look at the scenario. It's getting pushed by a force, then it's just going to coast along on a frictionless surface. Then block 1's going to hit some friction, which means it's going to feel a force resisting its slide. Then it's going to leave the friction, now move at should be a constant speed. Then it's going to hit and stick to block 2, and then they're going to move off together. What is that going to look like in terms of center of mass? So center of mass can be a little bit tricky. In fact, if they didn't put the word center of mass, if they just said for block 1, the graph is going to look almost identical, but there's going to be a small difference. If I go ahead and draw here, and I realize my face is probably covering up some of the stuff down there, but if I draw right here that this is block 1 and this is block 2, somewhere in between them, there's a point that we call the center of mass. It's going to be a weighted average of their positions based upon their mass. And since they have the same mass, it'll just be halfway between them. If block 2, in fact, I don't want to draw this over here. I'm going to draw it down below. If block 2 is stationary, as block 1 gets closer, like so, because block 1 has some sort of velocity, the center of mass is still going to be smack dab in between them. And that's the point that they want us to figure out and graph. That's center of mass velocity. Now, we have an equation to calculate the center of mass velocity as an actual number, but they don't want a number, they just want relative amounts. The key here is, what is it doing as time goes by? So when the plunger pushes on the block, it should have a constant force acting on it, which means it should also have a constant acceleration on block 1. And as it accelerates over to the right, it's going to also accelerate the center of mass. So the velocity of the block is going to increase, but that means the velocity of the center of mass is going to increase as well. So it should kind of go up. Don't know exactly what. Well, let's just label the graph first. How about we do that? From B to C, it's not pushing anymore. The plunger is no longer pushing. So that should just be a constant velocity then, because it's not speeding up or slowing down anymore. The block 1 is moving at a constant speed. The center of mass will be moving at a constant speed as well. From C to D, there should be a negative acceleration. It should be slowing down because of the friction, which means the center of mass would also be slowing down. From D to E, it should again be a constant velocity. And then from E to F, it should also be a constant velocity. After they stick together, they're going to move off of one velocity together. And so we need to figure out kind of relative where all those are. So for the constant acceleration, we just have to draw a line that's going a nice constant slope. So I'm going to have it go up 3 of these bars, bloop, like that. Doesn't have to, it could go up 2, it could go up 4, but I just decided to make it there because I know it's going to get up someplace, stay there, and then it's going to slow down, but it's not going to be 0. From B to C, it should maintain a constant velocity, so something like that. From C to D, it should slow down. So I'll just have it slow down 1 tick mark there. Not perfectly straight line, but it's close enough. Then from D to E, it should be a constant velocity, slower speed. But here's where that whole center mass thing takes over, because this is the collision point. That's where the 2 blocks hit and stick together. The question is, what's going to happen to the center of mass? Does the center of mass velocity speed up or slow down? And it doesn't. The center of mass, the idea of conservation of momentum is that there's some total momentum in a system before and after a collision, and the center of mass is what has that momentum. The center of mass of the objects has some total momentum, and because the total mass isn't changing, the center of mass's velocity doesn't change either. Once 2 things collide, the individual components may change velocities, but the center of mass stays constant. And so that means our graph isn't going to drop. It's just going to stay a nice constant velocity there. Now, if you drew your graph slightly different, if you screwed up that last little bit, you're going to lose some credit. But overall, this graph, for just looking at what block 1 does versus what block 1 and 2 center of mass does, is almost the same. It's only different at that last part. All right, let's take a look at part B. So they're asking when, if at any position, is the angular momentum of the sphere, in this case, going to change? Well, the angular momentum, if we take a look at it as an equation, L is equal to I times omega. And since the sphere isn't changing, the only way that we're going to change the angular momentum is if the angular speed changes. Well, what do we have to do to produce a change in angular speed? We have to have an alpha, and in order to get an alpha, an angular acceleration, we need to have some net torque on the object, which is a force exerted some distance from the pivot point. Well, if in this zone right here, there's no friction, and the force that's being applied is applied right at the center, right at the center mass of that ball. There's no force that's perpendicular to the surface of the ball. There's no, that is not directed in line with the, there's no force, mumbling there. There's no force that is tangent to the circle that's trying to make it twist in that zone. So from A to B and B to C, the force from the ground, normal force, would be pointing up like this. That's not going to produce a torque. The weight of the object going from the center isn't going to produce a torque. So there's no forces that are going to produce a torque on the ball. So from A to B and B to C, that's a nope and that's a nope. But once you get to point C here, the ball is going to experience a frictional force, and that frictional force is acting at a distance from the pivot, which is the center of the ball, and that's going to produce a net torque, which is going to produce an angular acceleration, which produces a change in angular momentum. For C to D, there will be an increase in angular velocity, so that's going to be our answer. Once it gets to point D, there's no longer any torque, still no friction there. So that means there's not going to be any net torque, no angular acceleration. It will have angular momentum now, but it's not going to have any changes at that point because it's frictionless thereafter. Now, all that stuff I just said, you would have to put into a paragraph somehow. But the idea that we have here on the screen is what's really important, that you're only going to get a change in angular velocity if you have some sort of net torque acting on you. And the only place you're going to have that is between points C and D.